In this video lesson, we're going to be looking at continuity. To help us understand continuity, we want to look at different types of functions. We want to look at polynomial functions, rational functions, piecewise functions. We're also going to be looking at some other functions. To help us understand continuity, where the graph is continuous, we need to consider the domain of polynomial functions, which if we identify a function as being polynomial, we're done with the continuity question because the graph is continuous on all real numbers. Okay, if we are working with a rational function, okay, the graph is continuous except for where we have zeros of the denominator. So if we have a fraction or a rational function, we really want to focus on the denominator and what makes the denominator zero. So the domain will include all x values that do not make the denominator equal to zero. So the rational function will be continuous on all real numbers except for those x values that make that denominator zero. When we talk about continuity and piecewise functions, we usually want to evaluate the restrictions, the x restrictions of each piece, and investigate continuity at x values of any breaks. We're also going to be looking at some other functions that are not polynomial, are not rational, and maybe not piecewise functions. And what we want to think about to answer the continuity question is, do we recognize the graph? Because if we do, that will help us answer the continuity question. Do we have a calculator to investigate the graph? Because that's always a good thing to do. And what else might we consider? All right, so let's look at this group of examples down here. Let's make sure that we're really paying attention to the language of the question and that we respond to the question appropriately. It says, find the x values, if any, at which the function is not continuous. Which of the discontinuities are removable? All right, and just real quick, removable discontinuities, you may recognize that as being a whole, or I like to call a whole a point discontinuity. So these three words, removable discontinuity, whole, or point discontinuity, all mean the same thing. All right, so we're trying to find the x values at which the function is not continuous. And then once we do find x values where the function is not continuous, are those x values going to be your wholes or point discontinuities? Well, I see 15 problems here before us. So the first thing I'm going to do is I'm going to look for polynomial functions. Problem 4, 5, and 6 are all polynomial functions. The exponents are whole numbers, and the coefficients on each term are real numbers. So it says find the x value at which f is not continuous. Well, the polynomial functions have a domain of all real numbers. So that means that there are no points of discontinuity on a polynomial function. So none here. There are no x values at which these functions are discontinuous. And think about the horizontal line at y equals 3. That just keeps going on. There are no breaks. And then this one right here. None. No x values or none will be fine. All right, are there any other polynomial functions? I don't see any. All right, so I'll just go back to problem number 1. Problem number 1, 2, and 3, all three of these are rational functions. And remember, the domain includes all x values that do not make the denominator equal to 0. So where would this graph be discontinuous? What's the x value at which f is not continuous or discontinuous? So we want to take a rational functions domain, and let's set it equal to 0. Well, right here that we see that if x's value is 0, then we would have an undefined situation. So my answer here is x equals 0. Number 2, set the denominator equal to 0, and if need be, solve. So add 1 to both sides. X cannot be 1, because if x is 1, that means we divide by 0. So let me go back to the question. Am I finding the x values at which f is not continuous? Yes, I am. Subtract a 5 to both sides. X equals -5 would be the x value at which this graph would be not continuous. If If you plug in -5, you're going to get -2 over 0. That indicates a vertical asymptote, and we'd have to lift our pencil there. All right, let's look at some more rational functions. Those seem to be pretty easy. Okay, 7, 8, and 9 are also rational functions, but it might require a little more algebra in solving the denominator for 0. So let's set x squared plus 5 equal to 0 and see what happens. So subtract a 5. Notice we get x squared equals -5. If we bring in the square root, we're going to have an imaginary number. So there are no real x values, okay, that when we plug in for x here would give us a 0. I mean, try and think of any number you could plug in for x, square it, which makes it positive, add 5 more, you'll never get 0. So how do we respond to this question? Okay, there are none or no x values at which this graph is discontinuous. All right, now contrast that with number 8's denominator. Notice this is x squared, but not plus a number minus. So I think we can, by inspection, real quickly see that if x is 3 or -3, we would get 0. But let's make sure that our algebraic work supports that prediction. So add a 9. So we get x squared equals 9. We bring in the square root. Come up here. Remember, a square root undoes a power, but it's an even root, so we take out the x but put absolute value around it. Square root of 9 is only 3. Remove the absolute value, and you get -3 and +3. So these are the x values at which the graph is discontinuous, or f is not continuous. I still have to be careful about qualifying which of these discontinuities, these x values, produce point discontinuities. Well, that's where we're going to have a common factor. So let's put that back up here. Point discontinuities occur where you have a common factor in the numerator and denominator. All right, well, let's just think about our work so far with our rational functions. So this denominator of x was not present in the numerator. X was not present up here, so I didn't have a common factor. X minus 1 was not another binomial up here, so I didn't have a common factor. X plus 5 is not present in the numerator to where I'd have the common factor of x plus 5. Look at 7. It didn't matter anyway. We didn't have to worry about a common factor because we saw that the only numbers that made your denominator 0 would be imaginary. So that means all real numbers are part of the domain of this function. X squared minus 9 factors into x minus 3 and x plus 3. But notice in the numerator, I have x plus 8. I don't have a common factor. All right, so let's come over here to this denominator. Let's factor it, x minus 4, x plus 4. Notice that I'm going to have a common factor that I'm going to divide out, and that's where we're going to get our whole, or point discontinuity. Let me first of all find the x values where this graph is not continuous. So go along our merry way, do the same thing we've been doing. Add 16 to the other side. We know our solutions are going to be positive and -4 once we do all the necessary algebra. So I'm going to put x equals -4 and x equals +4. Now before I leave this problem, I notice that x plus 4 and x plus 4 will divide out with each other. Well, the 0 of this factor is -4. What makes this common factor 0 is when x is -4. So we're going to call that our whole. I'd prefer to write point discontinuity, but it's too many letters. X equals 4 comes from this factor, but notice that there is not an x minus 4 factor in the numerator. So really what we're going to have here is what we call a vertical asymptote. And let's see how that would work numerically. It didn't ask me to qualify the vertical asymptotes, but I'm just going to kind of go ahead and extend here. If I plug in x equals 4 to this x in the numerator, I'd get 8. If I plugged in 4 to x in the denominator, I get 0. Any fraction that's not 0 over a 0 produces graphically at that x value a vertical asymptote. So that's just a little extra. All right, let's look at 10. It's a rational function, as is 12. So let's tackle these rational functions, okay? All right, let's find the x values at which the graph is not continuous by setting the denominator equal to 0. Subtract 1. Again, we get x squared is -1. So there's no real solutions, just imaginary. So that means that this graph is continuous across its whole domain. No x values where the graph is discontinuous. And remember, x squared plus 1 does not factor. That's a sum of squares. It's not a difference of squares. So I'd never be able to cancel the numerator with the denominator anyway, because it didn't factor. All right, let's look at 12. Rational function. I might want to try and factor it first. I'm going to have to anyway, because I'm going to set the entire denominator equal to 0. So this should factor pretty easily because a is 1. If you do your multiply add chart, okay, when you factor, we should have x and x, and this should be -5 and +2. You can check your work by foiling. Set each factor equal to 0. So from the factor x minus 5, I get x equals 5 as a solution. From the factor x plus 2, I'm going to get x equals -2 as a solution. So the x values that would make your denominator 0 is going to be -2 and x equals 5. All right, so let's think one more time before we leave this problem. I could factor this into x minus 5 and x plus 2. Notice that in the numerator, x minus 5 will cancel with that common factor down there. So at x equals 5, we have a whole. Now, x plus 2 doesn't have a common factor, so the solution is actually going to produce a vertical asymptote. And again, you could try plug in -2 for x. You're going to get -7 over 0. And again, that structure of a fraction with not 0 on top of a 0 suggests that you have a vertical asymptote on the graph of a rational function. All right, let's take care of number 11. Okay, again, we're trying to figure out the x values at which f is not continuous. It looks like a rational function, but it's not because of that absolute value. But that's okay. We'll handle it the same as we do with the rational function. I just want to focus on the denominator. Okay, and the x value that makes the denominator 0 would be -3. So is x equals -3 a whole? Well, come back here, sorry. Only if we have a common factor in the numerator, and it looks like we do, but that absolute value kind of throws things off. So it's a kind of a different situation. So remember back up here, other functions. Okay, do we recognize the graph? We should. This right here, okay, is the here and there. So shift the graph to the left 3, open circle off to the right at a height of 1, open circle vertically lined up here, down here at -1, off to the left. Is this a point discontinuity or a whole? No, this is a jump discontinuity. So because we knew what the graph looked like, we knew that we did not have a point discontinuity, we had a jump discontinuity. All right. So these are the x values at which we have breaks in the graph. Okay, let's go to 13 and 14. Let's look at these piecewise functions. Notice that in 13, y is equal to x as long as x is less than or equal to 1, and y is equal to the x squared graph, but only where x values are greater than 1. You can try and draw the piecewise graph. This should be an easy graph. However, both of these functions, x and x squared, are continuous across their whole domain. So the only place we have to be concerned about is, do these graphs come together at x equals 1? So let me evaluate 1 just real quick by inspection. Plug 1 in for x, you get 1. Plug 1 in for x squared, you do also get 1. So these graphs have the same y values at x equals 1. So it's, we have a linear function. So where x is 1, we have this linear function that looks something like this, goes through the origin. And then where x is greater than 1, we're also up here at a height of 1, then it's that parabola that just continues upward. So what happens is that these two pieces come together at the same y value of x equals 1. So we would respond and say there's no x values at which this graph is discontinuous. So on 14, let's do the same thing. Let's plug in x equals 2 to this linear function and plug in x equals 2 to this linear function. If we get the same y value, same answers, then the graph is just, it flows, it's fluid. There's no breaks in the graph. All right, let's plug in 2. A half of 2 is 1. 1 plus 1 is 2. Now let's plug in 2 here for this x. 3 minus 2 is 1. So the point 2, 2 is on the linear function, but the point 2, 1 is on this other linear function. So that's a jump discontinuity. So I would say the graph of this function is discontinuous at the x value of the break of 2. All right, and last but not least, 15. Okay, 15 is not a polynomial function. It's not a rational function. It's not a piecewise function. It's a different function. It's a cosine function. Well, let's think back to our previous study with cosine. We do know that cosine starts up here at 0, 1, and its domain is all real numbers. Okay, and it just kind of repeats itself. Well, that would be cosine of x right here. So what's happening in this equation to the parent function y equals cosine of x? Well, the only difference is I'm probably stretching it horizontally. So in that case, if I just made this graph wider, there's not going to be any x values at which even a stretched graph of y equals cosine x would be not continuous. So with at least the sine and cosine functions, their domain is all real numbers. You might remember that the other 4 trig functions, tangent, secant, cotangent, and cosecant, they all have vertical asymptotes on their graphs. So they would have x values at which the graph is not continuous, but we're asked about cosine, whose domain is all real numbers. So there are no x values on a break of this graph just because I'm going to horizontally stretch it or shrink it. Okay. All right, well, hopefully that helped you understand the idea of continuity and how to approach polynomial, rational, piecewise functions, and then some other functions as well.